Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video provides additional practice with some key concepts of binomial distributions. Let's get started. So here's our first problem that we're going to look at, involving a toy manufacturer that purchases bulk orders of AAA batteries. Each lot contains 2,000 batteries. Now, if the quality inspectors were to test all 2,000 batteries in a single lot, they would find that 2% of them do not meet specifications. However, we can accept the entire lot if no more than 2 in a sample of 50 fail the test. So what is the probability that an entire lot will be accepted? Go ahead, stop the video here, see if you can tackle this problem on your own, and then come back and we'll see how well you did. Okay, let's see how well you did with this. So, to find the probability that the entire lot will be accepted, we're going to go into StatCrunch and we're going to use our binomial calculator. We can use the binomial calculator because we meet the requirements for the binomial distribution. Okay, all the trials are independent. There's a fixed number of trials. The trials are independent, so they're not, the probability of one passing doesn't affect the probability of another passing. We've got all of the requirements for the binomial distribution met. So we can just go into StatCrunch and use our binomial calculator. So we put in 50 batteries, that's the size of our sample. The probability of success, 2%. Notice that we're defining success as failing to meet the specification. Again, we're just using the information that's given there in the problem statement. We want the entire lot to be accepted, but that means no more than 2 batteries can fail the test. So because the probability of success is failing the test, we're going to set this down here to less than or equal to 2 because we want no more than 2. So then we hit compute and out comes our requirement. So there's the sample size we test. There's the probability of success, which again is kind of a funky way of defining it, but it just makes the problem easier to work. We want no more than 2 successes, and so the probability that the entire lot will be accepted is a whopping 92%. Will almost all such shipments be accepted, or will many be rejected? Well, look at what we've calculated here. What say you? Well, I hope you said yes. About 92% of the lots will be accepted. So that means almost all of those shipments are going to pass inspection. They're going to be accepted. So the answer is yes. Let's take a look again at window contractor surveys. So we have a local manufacturer that's commissioning a survey of randomly selected construction contractors in the area. Found that 72% of them use their windows. So let's sample 6 contractors. What's the probability that exactly 5 of them use SureGlass windows? Again, we can put in our binomial calculator, put everything in, and we get that 5 of them, the probability that 5 of them use the windows, 32.5%. What's the probability that at least 5 use SureGlass windows? Well, notice here we've got to actually adjust the drop-down menu for our inequality sign there in StatCrunch. So we want to change that from an equals to greater than or equal to. Notice that changes the probability. It raises it, which we would expect because now we've got the probability of 5 and the probability of 6 added together. What's the probability that all 6 use SureGlass windows? Well, for this particular part of the problem, we're going to have to set that equal to 6, and then we get almost 14%. Notice if we add the first and the last of these probabilities, we get the second. That's what we would expect. Is it unusual for 5 of 6 contractors to use SureGlass windows? Well, no, it's not unusual because 32% is much greater than 5%. If we just use that 5% threshold, it's much greater. So no, it's not unusual. If the probability were less than 5%, then we would say it is unusual. But because it's greater than 5%, we're going to say it's not unusual. It's actually a usual expected value. Let's take a look at one last problem. This is something that actually happened in real life. A county clerk in New Jersey was accused of biasing election results by not randomly assigning line positions on voter ballots. So among 41 different ballots in that county, Democrats were assigned the top line 40 times. So assuming that the clerk wasn't biasing the election and that the assignments on the ballot were made at random, for looking at that top line position. So what limits separate values that are unusually low and unusually high? This matters because voters who go into the voting booth and don't really have a choice of something, there's actually an inbred bias inside the voter towards choosing whoever's listed first. So that's why this matters. We don't want someone using that inherent bias in the voting public to bias the election. So what are the limits that separate values that are unusually low and unusually high? Go ahead and stop the video here, see if you can work this problem on your own, and then come back and we'll see how well you did. Okay, let's see how you did with this. So first we're going to calculate the mean of the distribution here. It's a binomial distribution because you're either one, it's the top line either goes to a Democrat or Republican. It's one or the other. So here we've got the number of fixed trials times the probability of success. If it's not biased, we would expect that probability of success to be 50%. We would expect half the time it would go to one party, half the time it would go to the other. So that gives us 20.5 for our mean. The standard deviation we can likewise calculate. That comes out to be 3.2. Now we've got the values that we need to calculate for our range rule of thumb. So the minimum usual value is going to be 2 standard deviations less than the mean. That's going to give us 14.1. The maximum value is going to be 2 standard deviations above the mean. So now we've got the range of values that are quote-unquote usual. So then what is the probability that a random process would assign the top line to Democrats 40 times? Well, if we go into StatCrunch and use our binomial calculator, here's what we see. So 41 trials, probability of success is 50%. The probability that X equals 40 is going to be a number so low that it's practically zero. So what does that mean for our county clerk here in New Jersey? So is the result of 40 top lines for Democrats unusually high? Well, what say you? Well, I hope you said yes. I mean, look at the evidence that we have here, okay? So first of all, we can look at our range rule of thumb. 40 is well outside that range of usual values. So yeah, it is unusually high. But also you can look at the probability of getting 40 top lines out of 41 trials. The probability of that is practically zero. So you're looking at an extremely low probability event, and it actually happened. So according to the rare event rule, we've got to go back and question our assumption. Maybe these ballots aren't being made in a fair and equal manner. So what do the results suggest about how the clerk met the requirement to assign ballot line positions randomly? Well, we've just reviewed that. There's an overwhelming abundance of evidence here statistically that says, yeah, there's something screwy going on here. Okay, you've got that really low probability of this actually happening. You're well outside that range of usual values. So both of those results individually would suggest something's amiss. The fact that we have both of them together suggests the clerk did not assign those line positions randomly, that the clerk was actually biasing the election by whatever method was employed to create the ballots. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.